In our previous lectures, we've been talking about the three Newton laws of motion. Right. So now we want to express the second law of Newton in terms of momentum. In grade 11, we considered the effect of several factors acting on a body simultaneously. And the single force that has the same effect as the other forces acting together is the resultant force, or the net force. So that force that has got the same effect as all other forces, we call it the net force. Right. So we have to know that the force that acts on the box, right? For example, we are pushing a box, right? We call it the net force or the applied force. So if we are pushing something, or maybe we are pushing a trolley, or we are pushing anything, the Newton laws, they help us to understand the action and the consequences of forces. And all these three laws that we've been doing, the first law that does not take into cognizance the force, right, whereby we say the object will remains at rest, or the object will remains at a constant velocity in a straight line unless there is a net force that is applied to it, right? So you could see that the net force that is actually applied, right, will change the motion of the box. That force that we are applying, it will change the motion of the box, you see. So in the absence of this net force, the box will remain in its position of rest. Or maybe we are pushing a car, right? As long as there is no force, right, if we don't apply our force, right, the object will remain in its position of rest, right? And this is explained by the Newton's first law of motion, right, which states that an object will continue in its state of rest or uniform motion, or we can say constant motion, unless a net force is acting upon it. Then if someone, or when a force now is applied, we are now saying now there are two bodies that are now involved, right? It means now there are forces that are now acting in in pairs, and each body, it exerts a force. I gave an example when I was pushing that gyro, right? When I was pushing that, call it a stop nonsense or a gyro, we have got two forces, right? The action and the reaction forces. So we are saying the person, right, he exerts a force on the box, or on the gyro, or on the car, right? And this is what we call the action force. And then the box in turns, it also exerts anything that you're pushing, right? Even like if I push this table, right, it means like there is an action that I'm doing with my hand, and this table again, it will exert a force, right, or a reaction. So there are now two forces that are actually involved in the process, right? So this is what we call now the third Newton law of motion, the action reaction force. So we are saying if body A exerts a force on body B, and the body B is going to exert an equal but opposite force to force A, right? So it means the body can either speed up, it can slow down, or, right, if the forces are in equilibrium, it can remain as it is, or it can also change direction. So we say the body undergoes acceleration. The body undergoes, and this acceleration is directly proportional to force, and is inversely proportional to mass, like what we explained in the second Newton law of motion. Because the second law of motion, it says, or it states that when a net force acts on an object, right, it produces an acceleration. When a net force acts on an object, it actually produces a what? A net force. And that net force is the one that actually causes the acceleration or the movement, the running of an object. Right. So we are saying that the acceleration is directly proportional to what? To force. And is inversely proportional to mass. And we have to know that our boxes, they've got what you call, before we push anything, the box will be having what you call the initial velocity. It will be having the initial velocity. And then when we push the box, or when we push the trolley, then there is what we call the final velocity. And this usually happens after a certain time. So again, we can now come with a new equation. We want to come with a new equation. Remember, when we're talking about the second law of motion, right? We said force, right, is equals to mass times acceleration, right? That's first is equals to what? Mass times acceleration, right? That's what we said when we were doing our second law of motion, right? So now we are now saying, if you assume that the mass of the body is not changing, right? Then we can determine that the acceleration of the body. So we can now say the final, right? The final velocity, right? Since we said our body is having the initial velocity, so we are saying the final velocity, right, is equals to what? The final velocity is equals to the initial, right? Initial velocity plus acceleration times the change in what? In time, right? And then this means that if we want to get the acceleration, we want to now make acceleration the subject of the formula, then acceleration is going to be equals to the final velocity minus the initial velocity, you see, divided by what? Change in what? In time, right? But remember, from our above equation, we are saying the net force, or we can say the net force, is equals to mass times acceleration, right? Acceleration is a vector quantity. It has got magnitude and direction, right? And then now we can now substitute, right, acceleration now. So we can now say m, we said acceleration is the final velocity minus the initial velocity over the change in time. So we can now say force net is now equals to m times vf minus vi over change in time, right? So we know that this one, if we expand it, it's going to mv initial minus mv mass times volume final, right, minus mass times volume initial, right, divided by what? Change in time, right? And then so it means our net force, right, is equals to change in momentum over change in time, because mass times velocity for the final less mass times velocity initial, we get is the same as saying change in momentum. So the equation for representing Newton's second law of motion in terms of motion is this one. So we have now managed to come up with this equation. So this equation, it tells us, right, that the net force acting on an object is equal to the rate of change of momentum. So we are saying the net force that is acting on the object is equal to the rate of change of momentum, right? And then in this form, the momentum of the object changes, right? We are saying now if the momentum of an object changes, it is either the net force or the interaction time, according to our what? To our equation that we have created. Because we said now the net force is equals to change in momentum, right? And the change in momentum, we say the initial momentum, the final momentum minus the initial momentum divided by the change in time, right? So we are saying the change in momentum of an object can either be because of the what? Of the net force or the interaction what? Time, or both changes. So we can also represent the second law by the equation F net is equals to mass times what? Acceleration, right? Since we know that again this is also for the motion of the object, and we assume that the mass of the object, it remains constant, right, during the acceleration caused by the net force. So you could actually say that the Newton's first laws can also be extended into a general form. We know that the motion of an object can only change if the net force which is acting on the object changes, and that no change in motion is possible in the absence of that net force. So if there is no force that is acted on an object, the object does not move. But then if there is a net force, the object moves, right? So that's how we express the second Newton law of motion into momentum. So for those who need assistance in physics, you can call us on 078 196 5544. If you're outside South Africa, if you want to do online, you put a +277. So it's going to +27 78 196 5544. Or you can check us. You can send message on Messenger, or you can call us. Have a good day.